I'm very happy and honored to introduce our speaker today, and Dr. Waliser. And so, Dr. Waliser, I'm just going to do a very short introduction, because we are all looking forward to his talk today. So, Dr. Waliser got his bachelor degree from the Oregon State University, and also a master in the UC San Diego, and then a PhD in the and also in UC San Diego, yes. Right? And then Dr. Waliser is a senior research scientist in the water and carbon cycle group in the Earth Science section. Is that also the JPO? Okay. Yeah, and I think everyone should know that Dr. Waliser is very well known in the field of climate dynamics, and he's also made substantial and major contributions in climate dynamic studies. And also his research interests include seasonal variability and air-sea interaction and climate dynamics and modeling and prediction. And also recently, I think recent year, he has also done many important studies, especially in the MJO study, and allowed us to understanding and improve the modeling and prediction part. So today, sorry, this is my first time, so I'm a little bit nervous. I'm also very new. So today, Dr. Waliser is going to talk about cloud ice, a climate model challenging with science and the expectations of progress. So let's welcome Dr. Waliser. Okay.
Thank you. This is my first trip to Taiwan, and I really appreciate coming to speak to many universities. Frank, many of you know Frank, and he's helped set up these visits, and I got to spend Tuesday at NTU, and yesterday at Academica Sinica, and today at NCU, and then tomorrow at CWB. And yeah, it's great. And a fair bit of the talks I've been giving are on the MJO, because that is one of my interests, and if people have questions about that or want to talk to me about that, I'd be more than happy to describe that, or later maybe send you the presentation if you email me or something. And but today I'm going to talk about cloud ice, and this is some work that is going to appear in a special issue of JGR, and there's three of us at JPL that have helped sort of pull this work together, and it's myself and Frank Lee and Chris Woods, who was a postdoc at JPL for a while, and so we helped put this study together, but could have never done it without the aid of the modelers who provided us data and insight into how their model works, and then a whole bunch of people in the observation arena that provide observations of cloud ice. And for the most part, this talk and the research that we've been doing is to try and understand how to compare a model of cloud ice with an observation of cloud ice from satellite. And some things for remote sensing are very simple to compare. For example, sea surface temperature from satellite is pretty easy to compare sea surface temperature to a model. You don't have to think that much about it. There's some tricky parts, but it's pretty simple. For cloud ice, it turns out it's very hard to do such a thing, or you can't just do it without thinking ahead of time. There's a lot of particular things that you have to pay attention to in the satellite observations, and then in the way the models represent cloud ice. So for the most part, this talk is describing what you have to be careful for in comparing these two things. And these are some of the work that we've been doing, and the talk mostly covers these two papers and studies, and we'll briefly highlight some work that Frank's done with cloud liquid, which is sort of related to this topic. It's just rather than cloud ice, we're doing the same thing with cloud liquid. And then I'll show you some, just a couple slides from another study that one of our postdocs has done on the MJO in Southeast Asia using CloudSat data. So a lot of this theme is CloudSat data. And I should have actually put a slide in on CloudSat itself, but I didn't really stop to think about that. But How, do people know what CloudSat is? You think so? Really? That's good. Excellent. Okay, because I didn't know. Okay, so the motivation for why we started looking at cloud ice is here. This is a comparison of the IPCC models, the models that contributed to the last IPCC assessment, AR4. And this is for precipitation. And these are global average values. So it's just taking the global average precipitation from the 18 or so models from the IPCC assessment. And they're listed here, and that's how well they compare on a global annual average. And this is the same thing for precipitable water, and this is the same thing for cloud fraction. And for the most part, they agree relatively well, within 10% compared to the next one. And the notable thing here is that they've all had some satellite observations or observational constraints for a long time. So the models have had something to tune to and to get right. This is the same figure for cloud ice water path. So the total amount of ice in the column averaged down together. And so you can see that in contrast to these three, these differ by up to a factor of 20 or more. And even if you remove this big outlier, which was the NASA GISS models, they still differ by a factor of 6, which is substantially different than any of these. So given that clouds are really important to climate feedback and represent a really important aspect of climate feedback, it's really important that that agree better than it does. And so that represents a real problem. And there hasn't been that much observational constraints for cloud ice as there has been for these. So it's somewhat understandable. Okay, now this, I'm going to take the same data from here and plot it as a map. So these are long-term average, like from 1970 to 1990 averages from the IPCC models, from the current century runs. So this is from 16 of the models of the 20th century climate from the IPCC assessment. And this is just the ice water path again, the total ice in the whole column. And then the spatial patterns disagree a lot, but also the values, purple is 10, green is 100, and red is 1,000. So there's like 2 orders of magnitude differences here, which is substantial. And again, so that's the motivation why we thought we need to sort of look at this problem. And Frank's very good at looking at models and parameterization. We have people at JPL that work with the data all the time and can help us bring the two together. So that was what brought this study on. This is a comparison of some of the observations we have of cloud ice water path. This is from series MODIS. And so this is a MODIS product. This is a different MODIS product. And so those are using visible imagery. So they're just looking at how bright the clouds are and trying to ascertain how much ice is in the path by just looking at the visible image. Same thing with ISCIP, although they use some infrared data too. But these are all sort of visible and infrared. And this is a microwave product. Okay. And there is some level of agreement, but yet there's a fair amount of disagreement. So if you're a modeler, you might not have a strong, good feeling about how well these are measuring the observations. And so you might not feel too good about constraining your model to that. So there's been very little agreement between these products, and none of them have provided the vertical structure. So they're all just providing the total ice water path, and none of them are providing the vertical structure. So that's important. As opposed to, so when it comes to measurement strategies, if you consider this is our cloud, there's liquid down here, mixed phase, water and ice, and then there's these multi-layer products. That's the system that we're trying to measure. And those series MODIS, ISCIP products and so forth, they're just using passive techniques, just the radiation being emitted from the top. Okay, so either whether it's visible or infrared, and they have trouble finding out what's going on throughout the whole column because it's hard for the radiation to penetrate through the clouds. So it's very difficult for them to determine how much of this is ice and how much is liquid. It's virtually impossible. Or how many layers of clouds there are. One thing that happened in about 2004 is there was an instrument called the microwave limb sounder. It was aboard the Aqua satellite in the A train. And so that's the microwave limb sounder. And that used limb sounding through the top of the atmosphere like this. And it was able to resolve and measure cloud ice in the very upper troposphere. So that was one way that we had measurements of just ice and some ability to get the vertical structure. So that's one, but it doesn't get the total ice water path because it doesn't go all the way through the whole column. And then the best and most recent way is through CloudSat, which is a cloud radar, which penetrates through the column and then the signal comes back up when you detect the outgoing signal. And from that you can get vertical structure, you can get the estimate of the ice water content, meaning the amount of ice at any given layer, and then also the total amount, the ice water path. So the measurements that we've been looking at are mostly from CloudSat for this reason, that we can get the vertical structure and it's a solid measurement, and a bit also from the MLS microwave limb sounder. And then this ice water content is the amount of ice at any given place, and an ice water path is the total integral. And just so you have some appreciation, there's going to be a lot of comparisons between models and data. And just so you have some idea of what the resolutions of these are, think of this as a whole GCM grid box, like say 100 kilometers by 100 kilometers. The CloudSat is just a profile. It's just a one radar profile as it flies over the Earth, okay? And its footprint, its radar footprint, is about 1 kilometer. Well, 2 kilometers, 2 to 3 kilometers. So it just has one profile like that, and it would have many, many samples across 100 kilometers, just to give you an idea. And the microwave limb sounder has this long, sort of cigar-shaped sampling place that it samples. So, and it's very narrow, but it's very long. So that's sort of the spatial scales that we're comparing in these different measurements. And so these are the measurements that we had before, and then this is a version of the same thing from CloudSat. So this is CloudSat's version of ice water path. And that probably a priori is the most believable, and it's good to see that this one's not too far different from that. The main differences are maybe over the land, here and here and here, but otherwise it agrees fairly well. So one of them sort of agrees with CloudSat, but we tend to believe that one the most, and that's the one we're utilizing. And one of the reasons we care about using it the most is because it provides ice water content. So that picture I showed you before was ice water path, everything integrated together. This is ice water content at a specific pressure level. So we can now tell, oh, how much ice should be at this level as opposed to this level as opposed to this level. So we have more information. So this is a comparison of the amount of ice water content at 215 hectopascals between MLS, the microwave limb sounder, and CloudSat. And those don't agree that well, and that gets to the part of the reason we're having this talk and this study is to try and understand why. And then and this is looking at the same thing, looking at across the equator, latitude versus height, zonally averaged amount of cloud ice. And so this is what CloudSat provides in terms of the zonal average picture. And this is what, like I said, MLS only goes down so far into the troposphere, and it only captures this much of the troposphere. Otherwise, it gets down to where it's mixed clouds, liquid and ice, and it can't handle that. So that's what MLS will give you. This is the same data, just scaled differently. And okay. So now, so the main thing is this goal of trying to give the modelers a constraint, to try and give them an observation so that when they tune their model and develop their model physics for ice and clouds, they have something to compare to. So we want to use these measurements to do that. In order to effectively use these measurements, we need to know the following. Which cloud ice product is best? Those are the ones I showed you. And this is the main crux of the top. What do they mean by cloud ice? Okay. What range of particles sizes are being measured in the ice water content, both the model and the data? and what components of them are measured. So for example, a model may just represent the clouds, the suspended ice in the clouds, but the observation may be sensitive to the graupel and the snow that's falling as well. And so you can't compare the two. And that's the effort that we're trying to disentangle here. For example, this is for the models. In most GCMs, this is a typical AGCM, a typical GCM, like the ECMWF, the GEOS 5 NASA model, the NCAR CAM model, or most of those models, the IPCC models I showed you, their parameterization of clouds is such that they represent the amount of ice in the cloud, the part that's suspended in the cloud, and they do that because they think that that's the most important part for the radiation calculation. And that's why they keep it in the system and they keep track of it to do the radiation calculation. The other part that precipitates, they consider that not to impact the radiation so much. And so all the precipitation, they sort of just let it fall out of the column right away. So they decide this is going to precipitate, it's going to condense, precipitate, give off the latent heat, but I can just let it fall out right away. It's never suspended in the column. So the cloud ice-water path in those original diagrams are really just their representation of the clouds, the suspended part, and not the precipitating part, the graupel, the snow that may be in the cloud, within the cloud system as well. As where another set of models, and more sophisticated, for example, regional models and more sophisticated weather models on a regional scale might have several species that it keeps track of, like cloud, ice, snow, and graupel. And I'm going to show two examples in this talk of two models that represent three species like this. This is the NASA finite volume, that shouldn't say MF5, it should say MMF, multi-scale modeling framework, and the super parameterization version of the NASA model. And this is just another global model that has sort of high resolution, and that also has these three species. So for a model like this, which is rare for a GCM, a global model, it actually keeps track of all three species. So it keeps track of all different particle sizes, small cloud ice, bigger snow, and bigger graupel. As where most models just are sort of keeping track of a version of the small cloud ice. This is one of the first studies that we did, and Frank led this. This is a comparison of how well models did a few years ago at representing cloud ice. And this, at the time, we were using MLS data. And this is just to give you a quick idea of how well another set of models, not the IPCC ones, compare in terms of their representation of cloud ice. This was the observations, and this was about 8 different models at the time. And there was a fair amount of disagreement, and this is just additional reason why we kept at this line of research, because we needed to see these agree better. And the modelers, it was sort of interesting. If you, to most observation people, or people who are not modelers, they would look at this figure and say, wow, the models really are doing very good. But the modelers who sent the data to us, because they had no constraints and didn't know what the answer was, they looked at it and said, oh, it's not so bad, because they had thought it could be much worse. So it just depends which way, which side of the fence you're on. So some things that are important to consider. One is the spatial temporal sampling of your data when you're doing these model data comparisons. For example, the A-train. The A-train, remember, is this train of satellites that includes CloudSat, samples the equatorial region at 1:30 a.m. and 1:30 p.m. only. That's where many of the models we might compare to have the full diurnal cycle in it. So that has to be paid attention to, and I'll show you one figure that Frank did that showed how important that is. And this is really the crux of the talk, though. What range and particle sizes are represented by the observations, both in the model and the data, and what components of these hydrometers are measured versus modeled. It's sort of saying the same thing two different ways. So this is first, this example of this is from something that Frank did a couple years ago. This is just showing how important it is to consider the diurnal cycle in this process, and this is just for cloud ice. Different parameters have different level of importance, like sea surface temperature doesn't have so much of a diurnal cycle, although it does. This is the day-night combination, and this is the day-night difference. So this is the amount of difference between 1:30 a.m. and 1:30 p.m., which may not be the maximum difference in the diurnal cycle. It's just a difference in the diurnal cycle at a given point. And this is the same thing from CloudSat. But there is a substantial day-night difference, especially over land, because that's where convection has the strongest, diurnal cycle has the strongest impact on convection, and the convection is what's lofting the cloud ice up into the atmosphere. So from this, it would indicate that there is importance of sampling. So if you were going to compare, for example, CloudSat data to ECMWF analysis, you might want to take heed and pay attention to what time you're doing the comparison. And this is a more specific example of this. These are individual MLS observations. So these are the ground tracks of the satellite on a given day, one day in January 2nd, I believe, 2005. And the colored dots are places where it actually saw cloud ice. And this is the same thing, but then averaged to a 4x8 degree grid, which is what they do for their daily product. And this is the ECMWF analysis on the same day, but 4 times a day, every 6 hours. And you can see that there's a difference between, this is all 4 hours together, all 4 sampling times together, and this is when you've actually sampled the data just along the places that the satellite flew on that 1:30 a.m. and 1:30 p.m. And when the difference between those two is pretty remarkable in that the ECMWF is actually capturing most of the places that actually have, which is pretty remarkable because they don't assimilate that information. They assimilate other things that lead to that, but that's a pretty remarkable agreement for the analysis of that system. So given the difference between this and this, it would suggest it is important at times, at least for this quantity, to do that sort of sampling. Another thing that I want to point out, and this gets back to the main issue, is that any given measurement, remote sensing measurement of a quantity like cloud ice, rain, whatever it is, cloud liquid water, is always sensitive to a certain particle size, for example, or a certain range of variability that might be in the system. And what this shows is, for a whole year, this is a histogram of values of cloud ice between ECMWF and MLS. And so if you took, for the whole global tropics, every instantaneous value of cloud ice, okay, so this is, for the analysis, it's 4 times daily over the global tropics. You take every value of cloud ice and you make a histogram out of it. That's what you get with the yellow lines. As where the MLS data, which is this remote sensing data, is you would get this. And the reason is, if the cloud ice is this small, that's too small for it to detect. It's not sure if it's a small amount of cloud ice or just noise in the instrument and the algorithm, because every instrument has a certain threshold that it can detect. And that's MLS's lower limit of its detecting what it can detect. So in making this comparison, if you wanted to compare MLS versus analysis product, you have to be cognizant that the MLS or CloudSat or whatever it is can't measure the whole range of particles or ice water. So you have to consider the fact that MLS won't ever see these values. So for example, in the comparison that Frank did, so that's the lower limit of sensitivity. To make a fair comparison, we took all these values of ECMWF and just made them 0. So that it would be the same for ECMWF. And then that gave us something like this. So this gives an indication of some of these sampling issues. Here's MLS, the actual satellite value. This is the 4 times daily ECMWF, all 4 times averaged together. And these are for a whole year at 147 hectopascals. This is the impact of sampling, actually flying the satellite through the ECMWF data and only taking the samples at 1:30 a.m. and 1:30 p.m. This is the difference between these two. So this was the impact of proper sampling the diurnal cycle according to the satellite. And then this is what happens when you account for that sampling and you account for that, you account for this issue here. And so by doing all these steps, now you have a fair comparison between the two. Just showing sort of the level of effort that you sort of need to take and care in making a comparison between these two. And anyway, it led to that and some conclusions about that, but that's sort of now it's a historic version of ECMWF, so I'm not going to talk about it too much, but the comparison's not too bad. And it's gotten better actually since then. I'm going to skip this. So now let's go back to cloud ice and making comparisons between the satellite data and the models. I think now we're going to move more towards using CloudSat, because CloudSat gives us the whole column, right? And MLS only gave us the top, the very top, and we sort of want the whole column. And so these these are versions of models, DCMs, that actually just represent cloud ice, the stuff that's suspended in the atmosphere, or maybe slowly falling but not precipitating. NCAR CAM 3, GEOS 5, the NASA model, ECMWF. And then these two are two of the GCMs that have all three species, but it's only showing the cloud ice part of that. And so what we really want is a constraint on that. Okay? And what we have is this, CloudSat. And naively, or if you're not considering it too closely, you might say, well, that's cloud ice from CloudSat, the observations, that's cloud ice from the models. The models don't agree, they don't have enough cloud ice, and so that's a problem. But actually, the models are only showing the cloud ice. CloudSat is a radar, and it's sensitive to even the precipitating parts of the ice. So if it's hailing or it's snowing or anything, it's going to pick up everything. So this is actually showing cloud ice. This is showing ice, snow, and gravel. And so this is probably not alone adequate validation for that. And so we need to still come up with something for that. And the question is, and until, I don't know, we thought too much about it, we didn't really know if this is cloud ice and this is cloud ice plus the other stuff, how big is the other stuff? And there's not that many places you can look at that. And we sort of resorted to these two models. This is one of those GCMs that has all three constituents, gravel, ice, and snow. And that's the total. And there's not too much information out there that would describe whether these are correct or not. We really don't know yet. But anyway, this is one model's depiction of it, and the main piece of information here, along with the next one, which is the other global model that has all three components, gravel, ice, and snow, is that in both of these models, we don't really know if they're right, but in both of them, gravel and snow are a big contribution to the total amount of ice. Okay? And like I said, most GCMs don't necessarily carry them in the atmosphere for the radiation, but they do account for it in the late heating, which is what the discussion was in the class today, I noticed anyway. So back to this. This is the amount of, for these two models now, it's only averaged. This is gravel, ice, and snow, and so this is just a different picture of the same thing I just discussed. And this is all of them put together. And so what we're after is validation for this, or maybe this, and CloudSat. So the main thing here is all of these constituents, gravel, ice, and snow, make kind of an order one contribution to the total amount. And so it would be nice if we could slowly learn how to measure each one of those. But in any case, we have what we have. We have CloudSat. So can CloudSat actually be used? It turns out that CloudSat is sensitive to most of the ice in the column. So for a model that has all three constituents and carries all the ice, this could be a nice validation estimate for all the ice, if the model has all the ice. Okay? So for models that carry and model all the ice, you might actually have some validation measure in CloudSat to use for it. But there aren't that many models that carry that at this moment. But then, now on top of that, we'd still like a measure for this, because most models have this, most models need validation for this, all those IPCC models. Is there a way to sample this so that we can use it for validation for the just the cloud part. So that's the total, and CloudSat carries with it a couple other pieces of information. One is it tells you what it thinks are the different cloud classifications, like altostratus, altocumulus, stratocumulus, convective, cirrus. It tells you what kind of cloud type it thinks it's seeing, and it also tells you if it thinks it's precipitating at the surface. So at the very bottom bin, the return bin from the CloudSat near the surface, looks like it's raining, then it's raining at the surface. So there's a precipitation flag at the surface, and then the different cloud types. And so what we thought is, if we take these clouds and we remove the cases that are precipitating or convective, that'll take out the cases that have all the large pieces of particles, frozen particles, and we're left with just things in the sky, just the clouds. So if you take the total amount of cloud ice and you take out all the cases that are precipitating at the surface, you get this. If you take the total and filter out all the convective clouds, so you're bound to take out many of the gravel and snow, you'll get this. And if you take out both of those, and you're really stringent, you're saying, I don't want any cases that are going to have precipitation in the atmosphere because those will be the large particles. I'm going to leave just the stuff that I think is floating. You have this. So we think that this could be a useful preliminary estimate for just the cloud ice in a GCM. Okay? And if that's the case, we can, for example, vertically integrate this now and get the ice water path. Well, this is the same comparison. If I just look at this piece up here and this piece up here, I get this, and I'm plotting these three figures, but only looking at this piece up here in order to compare it to MLS, which is the same place. This is only above 300 millibars. Just to show you that MLS is so far up in the atmosphere, it's sort of measuring just cloud ice. And if we do that filtering, we tend to get good agreement between these two. The MLS, which we think is measuring just cloud ice, up that far up in the troposphere, and then these filtered versions. So these two sort of agree, which gives us confidence a little bit that that is a measure of just the cloud ice. Yes, so then we can, and then just to tell you what we did to the data, this is a description of how many samples we had to remove from the data to get that, and the upshot of that is we only removed about 10 to 20% of the samples. So of all the CloudSat clouds, we removed about 10 to 20% of them that were precipitating or convective to get that answer, which is here. Okay. So we didn't have to remove most of it. Most of it's still there. And that means that now given this is the last assessment, we might have a validation measure for the people who are developing the models for the next assessment. And if we integrate that quantity, we get this. So this now is at least our version of something that's observed that you could use to validate these models. So we can try and get that into the modeler's hands as they try and develop and improve their model for the next assessment, the AR5. And so anyway, we're working on it. So some of the models don't look too bad, and some do have challenges still. But anyway, now that's sort of a success, though, for CloudSat to have produced something that might be useful for the models like that. And this is a comparison of some more recent versions of the models. This is MLS. This is at a certain height. This is ice water content at 215 hectopascals. This is MLS. This is our filtered version of CloudSat that we think is just cloud ice. And these are three models that just have cloud ice. And they tend to look a little bit better than, for example, the comparison that Frank did 3 or 4 years ago. And so it just suggests that by having this data in the last few years, we've made some progress in getting the modelers something that they can tune to and make their models better. And this is just an example of the work that we did a couple years ago, that when we started, the ECMWF's cloud ice looked like this. And in working with Adrian Tompkins, who was very helpful with us and very interested in using the data, they eventually, and he already had the idea that they didn't have enough cloud ice in their model. But when we showed him the MLS data, he was now more convinced of it, and they made the changes that they needed to in their model, and they went from this to this, and then the agreement was much better. So the data are having an impact on the modeling community, in this case, the forecast, one of the major forecasting centers. Okay. Before I get there. That approach is one sort of simple approach, kind of subjective approach. Another approach to doing the same thing was done, this was a study led by a postdoc in our group, Christopher Woods. And another thing you can do to get at the same type of problem is that every time CloudSat retrieves an ice water content value, it also gives back the parameters for a distribution of what it thinks the particle sizes look like. And again, it's not well constrained because there's not enough information, but that's their estimate of what it is. So for example, they give you 3 parameters such that then you can produce this distribution of particle sizes. This is particle size versus the number concentration. And it can't quite, I'm sorry, there's a really thin line that you can't see there, which is the other side of the curve. But the point is that if you integrate under that curve, you get the value of the ice CloudSat's giving. And so we're just backing out and looking at the distribution, and then we're going to say, let's look at the large particles and the small particles. For example, some models, they try to represent all the clouds, and then they say, anytime we get particles above 100 micrometers, we consider that falling out, and we're going to let that precipitate. And so our clouds only have particles less than 100 microns. Everything else, we let precipitate out. Or, for example, in that MMF model that has 3 species, graupel, ice, and snow, at any given time, they have a distribution for graupel, they have a distribution for snow, and then they have a distribution for clouds. And so if we wanted to compare CloudSat data more specifically than we did before all we did was just add up all their clouds, all the ice together and compare the CloudSat. But now what we could do is we could take CloudSat values and say, well, let's just say all the stuff that's less than 100 micrometers and all the stuff above 100 micrometers. And then we can take the same thing for the model and do the same thing. Add up its ice that's less than 100 micrometers and what's greater than. And it's important to get the distribution right because it has impact on the way that the radiation's produced, or radiation interactions with clouds. So that's what we did. So we summed all these species together, these 3 curves, and then redivided it between 100, greater than 100, and less than 100. Same with the CloudSat. And this is just a methodology. It's just a demonstration of a methodology to compare models and data. And so this is the CloudSat data. This is 215 hectopascals from just 1 month. This is the ice water content in particles greater than 100 microns. This is the cloud ice in a small particle, less than 100 microns. And the fortuitous thing here, for example, is that PCMWF cloud ice tended to be modeled such that they kept particles less than 100 microns. And so the fact that these 2 agreed was another way of showing that their cloud ice was actually pretty good compared to the observations. It's a little more quantitative than the other method I just showed you. And in comparing to that finite volume one, which had all 3 species, and so now we're adding all 3 species back together and just dividing it between large and small. This is their large, if you're using 100 microns as a threshold, this is their large. This is everything above 100 microns. This is everything smaller than 100 microns. And you can see that most of their ice is greater than 100 microns. If you use a larger threshold, you can start to see that somewhere at about 300 to 400, they start to get stuff smaller, particles smaller than 300 or 400. And for the moment, that was sort of a shock to them. It doesn't seem wise to have your ice not have small particle ice. There's a lot of small particle ice in the atmosphere, and that's really important for radiation. And the fact that they don't have that in their model was sort of a surprise and not really a great thing. And so anyway, it's a useful thing that we got together with them and have been working with them to demonstrate this, because it's not obviously a good thing. And so the CloudSat was able to help us to do that with their model. And so we're still working with them to try and improve and make sure that their model's doing what it should. Okay, so that's pretty much everything about the cloud ice, the model comparison, and data. Why are we doing that time? When did I start? 3 o'clock? Okay, so I have like 5-10 minutes maybe? No problem. Okay, so I'm gonna actually maybe, let's see, what do I know Frank talked a little bit about the cloud liquid, right? Should I go over that, or? I'm gonna just, you covered this, right? No. I could, we're doing essentially the same thing with the cloud liquid, Frank is. And so this is the same picture I showed you before, but now with cloud liquid rather than cloud ice. And the picture is just as bad. You can see it's still 2 orders of magnitude different. And so we're trying to work with the models to do the same thing. One thing that's also different for cloud water than is for cloud ice. The cloud ice observations from satellite tended to have better agreement between the different satellite observation products, even though they were different. Their overall agreement was not so bad. This is a comparison of the liquid water path between 4 different products: CloudSat, the Series Motors project, SSMI, and ISKIT. And these are sort of remarkably different. And this one is really different. And most people, from what I gather, that know this field well, tend to like and believe that this is probably the most accurate, even more so than CloudSat. And we're still trying to disentangle what this is due to. And if you separate out the precipitating liquid water, the cases that have precipitation at the surface, this is the amount of liquid water in those cases. This is the ones that are non-precipitating. And you can see that these features, which aren't that well represented or don't show up there, tend to be from these precipitating cases. And it's actually thought at the present that these, at least to some degree, are just artifact anomalous, not correct. Because the CloudSat radar is sensitive to the particle size, like R to the 6th or something like that. And so drizzle and precipitation can really impact the signal. And so this may be misclassified as too much liquid water than it should. This is but the challenge in the modeling world is at least as great. And this is the liquid water path values from 3 different models. Is this the liquid water? Yeah. The NASA model, the analysis, another NASA model. Oh, these are 2 different analyses. The NASA analyses, the ECMWF analyses, GEOS-5 simulation, so that's a climate simulation, the NCAR model, and this finite volume model. And you can see this is much bigger. If you look at the total averages, you can see that there's just a lot more liquid water up here in the atmosphere in the NCAR model than for the others. And part of the reason is many of the models use a very simple way of keeping track of the total amount of condensate, the water plus the ice as one amount. And they let it go through the atmosphere, and then at some point, based on temperature, they divide them up. So if it's colder than some temperature, they put most of it in ice. If it's warmer than some temperature, they assume it's liquid. And with the NCAR model, they use a threshold that's much colder than other models, like minus 40 degrees. And so that's why we think that that's off. But I'm going to try and speed up. I know Frank showed that, but didn't show this. So I'm going to show you one brief study of using CloudSat data for a more of a phenomena, in this case the MJO in the summertime, and what you can do with it in terms of looking at a specific feature. And so this is a typical occurrence of an MJO event in boreal summer over Southeast Asia, and then you have the anomaly. This is positive anomalies in rainfall, and they tend to go eastward. You see this blob move eastward, but yet it also moves northward too. So it develops here, and then it slowly moves up into Southeast Asia, right? And that's a typical pattern that you see for intraseasonal variability for Southeast Asia during boreal summer. In that there's both an eastward propagating component, and if you look at any given longitude range, it looks like it's propagating northward. And Duane, the postdoc in our group, he's really interested in this northward propagation. And he has done some theory on why there is northward propagation, but in this case he's just interested in the data. And so this is a composite of rainfall over a certain longitude range from 80 to, I think it's 95 east. So it's just a portion of this strip right here. And this is showing the northward propagation of those features. And with that, he took the CloudSat data and then examined for that northward propagating system. There's a whole bunch of maps behind this because there's 8 different cloud types. Then there's the cases that are precipitating and non-precipitating. And what he did is he followed at every given point, he looked at what the clouds were as that propagated north. And this is just a quick summary, and it's the last slide, I think. And so, but it has a few points on it. So, as that thing propagates north, there's always a center of the rainfall, and everything here is relative to that center of rainfall as it propagates north. So this isn't necessarily, this is relative latitude, north and south. Not absolute latitude, it's relative latitude to the maximum rainfall. And the left side is liquid water content, and the right side is ice water content. And so relative to the maximum rainfall, you get maximum liquid water at low levels ahead of the convection, ahead of the peak rainfall. And then the ice water content is mostly right over because that's where the convection is, putting the ice in the atmosphere. And then most of this, and this is where there are many maps, but this is just a summary, but most of this liquid water content is associated with precipitating stratocumulus clouds. Right? And most of this in this region is due to non-precipitating ultracumulus clouds. And then in this region, most of this ice, some is due to non-precipitating altostratus, but most of it is due to deep convection in that ice. And so you can distinguish what kind of clouds and cloud types there are for using CloudSat data. Anyway, he's writing that up. That's my summary, and the summary is mostly just about the cloud ice. Climate model cloud ice and liquid fields exhibit wide disparity. You saw that, and it's not really arguable. The CloudSat data and supporting related satellite retrievals are providing model constraints that have not ever been really available before, so there should be improvements in the coming years on how models represent these features. This is this notion that it's vital when you do a model data comparison with satellite data and a model, you know which is being represented by both. And are you really comparing apples to apples and oranges to oranges? And in this sort of analysis, I tried to demonstrate what you might need to pay attention to in making those comparisons. That's the same thing, more or less. CloudSat data, just off the shelf, cannot be used to validate most GCM cloud ice and liquid water fields just off the shelf. You have to be really cautious about how you make those comparisons. I don't know if many of you know about what's called a CloudSat simulator, or the cloud. Have anyone heard of the ISCIP simulator, where you take a model, you take the model ice and cloud fields, and then you simulate what ISCIP, for example, would see in terms of the cloud field by looking at the radiation field exactly the way the satellite would see it. And so you output the data just the way the satellite would observe the model. CloudSat has the same sort of simulator where if you hand it the clouds, it'll simulate what the radar would see flying overhead in space. And a lot of people indicate that maybe that's a great way to do the model data comparison. This is just a statement that it's not. If the model still doesn't represent rockle and snow, it doesn't matter because the simulator won't have that in it and you can't really compare the two anyway. So, despite all those things I just said, CloudSat data will lead to improvements in modeling, and I tried to demonstrate that through the impact on ECMWF and some of the other models. And then this is just an indication of the work that Shannon, that work I was just showing you, or Frank's Tibet work over the Tibetan Plateau. It'll have remote sensing of cloud-related processes in the monsoons, very heterogeneous contact, meaning it's got land, ocean, and snow, and topography, has been a challenge. In remote sensing, it's hard using just visible data to look at those features, but by using many different aspects, microwave, radar, and visible infrared radiation, we can probably make improvements in these sort of features of the monsoon. And CloudSat in particular offers a lot of advantages that haven't been there before. So anyway, this is the goal of one element of our group in trying to improve that. And that's it. Oh, that's it. Thank you.
Okay, question time. Anyone? Question?
I also have one more slide I want to show after, just to make sure there's no questions.
Okay, sure now.
Okay, so I don't have a chance to make you guys aware of something, but
Yeah.
I don't know if anybody's familiar with this, but I'm partly responsible for this, and I'm trying on this trip to make you all aware of this activity. It's something that developed over the last couple of years, and it's sponsored by WCRP and WWRP and Thorpex. And it's a program designed to improve tropical convection and weather and climate models. And it's sort of like, for some of you, none of it in the back, but maybe a couple of you in the front might remember FIGI, the first global GARP experiment, where in 1979 they sort of added extra instrumentation, and for a year they had sort of a specialized year of observations. This is sort of along that lines, and then we're trying to, for a year, from May of this year to 2009, about October 2009, get a very enhanced data set put together of high resolution analyses and all these satellite products, and then the ongoing field programs within that, and then make some very specific research focus on the tropical convection events that occur during that year. So it's a focused year approach to looking at tropical convection, and it will utilize high resolution models to a great extent to try and improve parameterizations of convection. And have the science plan's available for anybody interested. I can send it as a PDF, and we're trying to just make people in departments aware that they can contribute to that and take part in that, and try and, there will be data sets available between that time period that if you use and you study the phenomena during that year, you will by implicitly be contributing to the program. And eventually we'll have a website that's more interactive and a more interactive community to take part in. But just try and keep your eyes and ears open if you're interested in this, and you can write me and I can provide you more information and so forth on it. Okay, that's what I wanted to say.
Maybe I got one question.
Okay.
About when you look at when you compare the cost and ice, the distribution with the model, and you also mentioned that the cost, that part is sensitive to things that actually from
Precipitate.
precipitating. And is that the reason why when we compare with the model, it seems that the location of the crusted ice is more close to the ground compared to the models? Because
I want to go to a figure to see which one you're looking at, because
the meridional distribution.
yeah, I know which figure you mean. That
That's
one?
similar, this one. So if you compare with the other.
Oh yeah, that's a good question. So that might show it best on this. I mean, because we've taken, this became this, once we removed what we thought was the precipitating part and the convective part. So for example, some of this looks like it's probably due to the snow and the gravel. Is that sort of addressing your question?
Yes.
I mean, and this, for example, this goes away. And that's probably that deep cumulus convection that's been precipitating at high levels. So you can see that once you get rid of the take just the non-convective parts, that goes away, for example.
And I'm just curious, so what did ECMWF do to correct? How did they?
Oh, there were two things that one was they allowed, well, there were two things that sort of look like they compensate each other. Like, but he made a change to the model physics for ice. One was that he allowed ice-based supersaturation, which would suggest that you would get less ice, right? I mean, because now you're going to allow supersaturation conditions in the environment and sort of not allow the water vapor to be on the ice. You're allowing it to be supersaturated. That's just one change. But then there was a compensating change to reduce the ice sedimentation rate. So rather than ice falling out quickly, it stayed in the atmosphere longer. This is just the actual clouds. And so the clouds would sediment at a slower rate, and so that you would keep more ice in the atmosphere. That's the one of the two changes. One leads to less, one leads to more. But that one ended up compensating more and producing more cloud ice because you left it in the atmosphere longer. Does that help?
Yeah. Thank you.
But that's a cycle. That's probably like 2 cycles past now. I mean, they make changes every 6 months or a year or so.
And how long do they? How long the data do they use to compare with the cost and times?
Oh, in that case, all they had was MLS data. And they weren't really.
I mean, how would I know? Like, sometimes it's because of the model ice and when comparing to that pattern that I want to tune to.
Oh, in this case, it wasn't. That's probably. They didn't have the virtue of making really good comparisons because their skill, the requirements to put in a change in the model. The measurements for that are so many different things, the metrics in terms of forecast skill, that, all he was probably looking for was to make sure that this color, blue, looked a little more green than it did before. But, because the details, he didn't have the virtue to make every detail right. So he was probably just after getting an order of magnitude improvement.
In fact, Adrian did tell me that the radiation budget does improve a lot with the new cycle. Meaning the ice, growth of the ice, improvement of the ice has helped for radiation budget.
Yeah, so even though maybe the ice looks better, it may not look perfect, it looks better, but also then it made improvements in another bunch of other fields, like the radiation. So as a whole, it's sort of a variational analysis to get the most things best or better, and then say that's an improvement and make the new cycle of the model. So.
Sorry, maybe I shouldn't ask this question, but for me, for a forecaster, how much if I spend this effort to tune my cloud ice, and what should I expect, like which part of my prediction should improve, and how much would you expect to improve?
Yeah, there's a I don't know what the exact answer is here in terms of improvement, but there's one motivation that I know, like we see, short of making a prediction improvement, if those guys are convinced that physically their model is better, because the cloud ice matches better and the radiation matches better, they might make the change and get no forecast skill improvement as long as they don't get a degradation. So they might have made the change in spite of getting no improvement, but no degradation, but with the certainty or knowledge that their model's physically better, so that the next changes they make, they're making it with a more consistent model. Does that make sense?
Yes.
Okay, I mean, so, yeah, and I don't know if there were specific forecast scale improvements. Overall, every new cycle improves something, and there's many changes that could go into it. So you wouldn't necessarily maybe know if your improvement in cloud ice was the thing that made the improvement or not. So some of it is just based on making the model what they think is just a better model. And I don't know the details for that particular cycle as to what they think, but it's good, very good question.
Sorry, it's a sort of naive question.
No, it's a very relevant question.
Thank you very much, and let's thank Dr. Wong.